Building construction for the fire service, week 5, homework problem. I guess it would be homework problem number 6. It's the first in the additional problems after problem 5. In this problem, they're asking you to find the resultant of this combination of vectors. So 2 times vector A negative 2 times vector A, negative 2 times vector B, and negative 3 times vector C. Well, let's think about these just in magnitude first. Forget the sign for a moment. Just think about this 2. What is it saying? It's saying we want a vector that is twice as long for A. But remember that the length is just representative of the quantity. So I can just simply strike the 120 and replace it with a number that is twice as much. So now we're looking at a 240-pound pull. For vector B, same thing. Strike the 160 and write 320 in its place. And for vector C, strike the 100 and write 300 in its place. Now, the minus signs are a bit confounding because what that means is when you see a minus sign in a vector, you can think of it as flip the arrow, flip the direction of the arrow. So now this is the tail on this end of this vector, and the head of this vector is here. This is the tail of this vector here. The head of this vector is here. This is the tail of this vector here. The head of this vector is here. So really, at this point, you're probably better off to redraw this as a new combination of vectors. So we have vector A, which is pulling down and to the left now because it's negative, with 240 pounds force. And if you think about projecting through the center, that means that you're going to come out 180 degrees from where you started. So if you started at 37, this angle all the way back to the start at 0 degrees is going to be 180 plus 37. Well, that may get a bit confusing to look at in the picture. And so really probably what I'm more interested in finding is this angle. And this is basically covered under similar angles theorem that you probably learned in elementary school math, that when one line segment crosses another, the angle is reflected across the vertex. So we can just by that property say that this angle is 37 degrees. And let's look at now, that's vector A. Let's look at vector B. Vector B is pulling down and to the right. It's pulling this way. And what do we know about vector B? It's at 143 degrees. Well, here's 90 degrees. So what does that mean? It means it's 53 degrees past that. So this angle here, 53 degrees. But I know this entire angle is 90, so 53 minus 90 minus this 53 is 37 degrees here. So let's think about, as this vector B projects on through, what angle is going to be reflected across the origin? This 37 degree angle here. So this angle is 37 degrees. And the last vector, vector C, where's vector C working? Vector C is pulling up and to the right. And I should probably label these. So this is vector C, this is vector A, this is vector B. And let's think about the angle of C. C is at 240 degrees. Well, this is 270, which means that this angle here is 30. So as we look at vector C, it's 30 degrees from this 270 degree angle here, right? And I know this is 270 because it's 90 plus 90 plus 90. And it's 240 to here, which I guess was given. Or the other way to think of it is it's 60 from this other horizontal line here. So I know the angle of this. So let's think about reflecting that through the origin. That 60 degree angle now is going to be here. So I know this is 60 degrees. And again, magnitudes. The magnitude of vector B, because we're multiplying by 2, is 320 pounds. The magnitude of vector A, because we're multiplying by 2, is 240 pounds. The magnitude of vector C, because we're multiplying by 3, is 300 pounds. Well, now this is just a matter of plug and chug using basic trigonometry. Easy for me to say. So let's think about vector A. Let's break it down into its horizontal and vertical components. There's a vertical component, and I'll call this vertical component y of A, the y component of A, and this is x of A. And again, the magnitude of A we know is 240 pounds. So that's represented by the hypotenuse. Now, we're probably interested in finding one of these included angles, and the easy one to find is going to be this angle up in here. It is the complement to that 37 degrees, which happens to be 53 degrees. So if I look at the x value, the horizontal component of A, which is pulling leftward, we need a function that relates the angle of 53 degrees to the hypotenuse and the opposite side. So we think about trigonometric functions, so, ka, toa. And what relates the opposite side and the hypotenuse? That's the sine function. So, sine of 53 degrees equals opposite, which is the x component of A, over hypotenuse, which is 240 pounds. And then we simply multiply both sides by 240. We get 240 times the sine of 53 degrees equals the x component of vector A. And at this point, it's just an exercise on the calculator. So 53 degrees, we'll take the sine of that, times 240. We're going to call that about 192 pounds. Okay, so this is 192. Now, we could develop a new free body diagram. So we're going to start out, and this is going to get fairly complex because we've got a lot of vectors here. So I'll label each of these contributions. This is the x component of A, 192 pounds to the left. The y component of A, then we got to relate the adjacent side to the hypotenuse. That's going to be a cosine function. So cosine of 53 degrees equals adjacent over hypotenuse, the y component of A, over 240, multiply both sides by 240. 240 times the cosine of 53 degrees equals the y component of A, and again, simply an exercise on the calculator. Or if you had a chart of the trigonometric functions, you could certainly figure it out that way, but the calculator makes quick work of it. And we'll call that 144 pounds. So if you look at the y component of A, it's in the downward direction. So we will draw a vector coming down. We will label it as, this is the y component of vector A, and it's 144 pounds. Now, vector B. Vector B is down and to the right. So let's diagram that. That means it has a downward component and a rightward component. It has a magnitude of 320 pounds. And this included angle here, well, that's going to be the complement of the included angle we figured out. So we would need to figure out this angle, but that we've already figured out is 53 degrees because the two of them need to add to 90. So there's a 90, this is 53 degrees. This is the x component of vector B. This is the y component of vector B. And how do we relate these two? Well, let's take the x component first. The x is opposite, and we're trying to relate it to the hypotenuse. So again, sine of 53 equals the x component of vector B over the hypotenuse, which is 320. Multiply both sides by 320 pounds. 320 times the sine of 53 is the x component of vector B. So 53 degrees, we're taking the sine function, multiplying it by 320, and we will call that 256 pounds. Now, if you look at that x component, it's to the right. So as we come over to our free body diagram, this is the x component contributed by vector B, and it's 256 pounds. The y component of vector B, that's the adjacent side related to the hypotenuse, so that's the cosine function. Cosine of 53 degrees. What is it equal to? It's adjacent over hypotenuse. The y component of the B vector divided by the hypotenuse, which is 320. Multiply both sides by the length of the hypotenuse, which is 320. You get 320 times the cosine of 53 degrees equals the y contribution of the B vector. So again, 53 degrees, take the cosine, multiply it by the effective length of the vector, which is 320 pounds, and we find that that's about 193 pounds. And if you think about this y component of the B vector, it is downwards, so we will stack it right on the end. The y component of this is y component of B, 193 pounds. All of these units are in pounds here. Okay, last step. Now we need to look at the x and y components of vector C. Vector C projects up and to the right with a magnitude of 300 pounds. It has an x component that by definition is perpendicular to its y component. And let's think about included angles. Well, we know this included angle is 60 degrees. There's this y component of vector C. There's this x component of vector C. And now we just need to relate the two of them, the three of them. So the first thing is, let's try and figure out this x component. There we need to relate now an adjacent side to the hypotenuse. So that's the cosine function. Cosine of 60 degrees equals adjacent over hypotenuse, the x component of the C vector over the 300-pound hypotenuse. Multiply both sides by 300. 300 times the cosine of 60 degrees equals the x component of the C vector which is take 60, we're going to take the cosine of 60 degrees times the magnitude of the vector, which is 300 pounds, and the x component is going to be 150 pounds. And if you think about the direction of the x component, the direction of the x component is to the right. This is the x component of vector C, 150 pounds. And last but not least, we need to find the y component of vector C. Well, y is opposite in hypotenuse, so sine of 60 equals y sub c over the hypotenuse of 300. We'll multiply both sides by 300 and we will get a value for y sub c. C pushes upward, so y sub c is going to be oriented in this direction with a value yet to be calculated, which I will calculate in the continuation of this video.